In this video, we are diving into one of the most fundamental equations in quantum mechanics, the Schrödinger wave equation. Let's break it down and understand where it actually comes from. Now, why do we need a new equation at all? Classical physics could not explain the behavior of particles like electrons inside atoms. That's where quantum mechanics has stepped in, and Schrödinger proposed a wave-based description of particles. In the year 1924, de Broglie suggested that particles like electrons also behave like waves. The wave function, denoted by psi, describes the probability amplitude of finding a particle at a given position and time. Now, before we step into the derivation, let us know a few terms. Planck's constant, that is h bar simply equals to h over 2 pi. Del operator means partial derivative. Let's begin with a plane wave traveling in one dimension. The general form of the wave function is psi xt equals a times e to the I kx minus omega t. Now, kx can be written as 2 pi over lambda times x. We know that lambda equals h over p. Therefore, 1 over lambda can be written as p over h. So, this equation can be written as 2 pi times p over h times x. Now, let us bring this 2 pi into the denominator, which gives us p over h by 2 pi times x. Now h by 2 pi is equal to h bar. So this is p over h bar times x. Omega t can be written as 2 pi times f times t. Now we know that E equals h times f. Hence, f can be written as E over h, where f is the frequency. Therefore, this equation can be written as 2 pi times E over h times t. 2 pi over h can be written as 1 over h bar, so this gives us E over h bar times t. Therefore, the equation can be written as psi equals a times e to the I px over h bar minus et over h bar. We can further write this equation as a times e to the I over h bar times px minus et. Now let us perform a partial derivative of psi with respect to time, which gives us dou psi over dou t. This simply means partial derivative of psi with respect to time equals a times e to the I over h bar times px minus et, because this is an exponential term, times. Now we need to perform derivative of this term, that is I over h bar times minus et, which gives us minus e over h bar times I. Now we can multiply and divide this term with I, which gives us minus e I squared by I h bar times. Now this whole term can be written as psi because this is the same term. Now we know that I squared equals negative 1. Negative 1 multiplied with the negative gives positive. So this can be written as psi times e over I h bar. Now from this equation, we can write the value of E psi as I h bar times dou psi over dou t. This is one of the relations we are going to be using in the equation. Now let's get back to the equation, that is psi equals a times e to the I over h bar times px minus et. Now let us perform a partial derivative of psi with respect to x, which gives us dou psi over dou x equals a times e to the I over h bar times px minus at, because this is exponential, and the derivative of this term, that is I over h bar times px, which gives us I over h bar times p. Now this term is simply psi, so you can write this as psi times I p over h bar. Now let us perform a second partial derivative of this same equation, which gives us psi times, now this is a constant term which will be repeated again, so this gives us I squared p squared over h bar squared. I squared is -1, so we can write this as minus psi p squared over h bar squared. From this equation, we can write the value of p squared psi as negative h bar squared times the second partial derivative of psi. Now we know the total energy of a particle is equal to the sum of its kinetic energy plus potential energy. Now kinetic energy can be written as half mu squared plus potential energy can be taken as V. This equals p squared over 2m, because kinetic energy can also be written as p squared over 2m plus potential energy. Now let us multiply the equation with the wave function. So this gives E psi equals p squared psi over 2m plus v psi. Now let us substitute the values from the previous results into this equation, which gives us I h bar time derivative of the wave function equals negative h bar squared over 2m, this 2m is written in the denominator, times spatial second derivative, that is this term, plus v psi. Now this is one of the forms of the Schrödinger wave equation when the particle is considered to be moving in one dimension. If we consider the particle moving in 2 dimensions or 3 dimensions, we can take multiple variables. Now in 2 dimensions we have x and y, in 3 dimensions we have x, y and z. So the equation can be written as so. Now we can write this term as so. This term you see here, this is known as del or del operator, which basically stands for the second spatial derivative. So the equation can be simply written as this is the Schrödinger wave equation that is time dependent in 3 dimensions. As you can see, we have the variable of time here, so this equation is time dependent. It governs how the wave function evolves over time. Thank you so much for watching. Be sure to like and subscribe to our channel for more such informative videos.